喂，喂，可以听到吗？喂，好的，大家上午好，我们现在就开始今天的研讨会。首先呢，欢迎大家。我是奥泰尔的 CFD 工程师，我叫武龙。今天的研讨会呢，就由我为大家来主持。首先感谢大家在百忙之中抽出时间来参加这个网络会议。那么今天讨论的主要内容是关于奥泰尔在风扇噪声方面的最新解决方案。那么风扇噪声呢，使用了奥泰尔其中一款 CFD 专用的软件模块，叫 ultraFluidX。而风扇噪声也是 ultraFluidX 在2020版中最新推出的旋转网格功能基础上开发完成的。那么今天的演讲嘉宾呢，是奥泰尔的高级技术总监 Kevin Ghosh 先生。Kevin 是奥泰尔专门负责空气动力学、热管理和气动噪声解决方案的全球技术专家。那么关于他的专业背景呢，在接下来的演讲中，公司负责亚太区 CFD 业务的副总裁 Frank 吴先生也会为大家做详细的介绍。那么由于网络连接不是特别稳定，那么为了使本次会议呢进行得更加顺畅，Kevin 事先已经将演讲的内容呢录制了视频，我们会在会议开始的前30分钟为大家播放这段视频。Kevin 本人呢也会全程在线参会。会议的中间和最后呢，我们都留了互动问答的时间。如果大家有任何问题、意见或者建议呢，都可以在互动环节中提出。那么 Kevin 也会在线尽量为大家解答。那么接下来就进入今天的主题，由 Kevin 为大家分享奥泰尔基于 ultraFluidX 的风扇噪声解决方案。
I'm delighted to present to you Mr. Kevin Ghosh, our speaker in today's webinar titled Predicting and Minimizing Fan Noise in Industrial Equipment. Kevin joined Altair in December of 2018 after 20 plus years of experience in the area of aerodynamics and aeroacoustics. He brings senior level simulation as well as experimental expertise. Starting at GM's Racing Group, then as chief engineer at Navistar, and later as manager of the North America Technical Field Organization at EXA Corporation. He brings extensive expertise in cars, SUVs, racing, and heavy trucks. At Altair, he leads our aeroacoustics business development and validation efforts, co-author of several papers in the area of aerodynamics, and owner of 2 patents. And without further say, Mr. Kevin Ghosh.
Good morning. I am Kevin Ghosh, Senior Director of Global CFD at Altair. I am here today to present predicting and minimizing fan noise in industrial equipment using ultraFluidX. As you can see in the video that is now playing, the fan noise I'll be discussing is not going to be limited to simple bench tests or chamber testing of isolated fans. But in many cases, the fans are embedded inside enclosures with a very complex under-hood environment. Not only is the technology being used to evaluate and understand the acoustics, to develop and validate designs, but it is also being used to understand the complex flow structures, their interactions, and other design imperatives such as powertrain cooling. Today's agenda will roughly be broken up into 4 sections. First, we'll quickly discuss fan noise itself, why it's challenging to simulate, and why simulation is important. We'll also mention different collection methods and post-processing steps that can impact the comparisons of different results. Second, I'll be providing some background on ultraFluidX. Here I'll explain a bit about the Lattice-Boltzmann method, the main features of ultraFluidX, some of the advantages that provide for rapid turnaround of fully time accurate simulations, and a quick glimpse of the tools. Third, I'll provide insight on how the data generated from ultraFluidX is post-processed into meaningful quantitative and qualitative data that can be used to better make design decisions. And lastly, fourth, I'll walk through several actual case studies across multiple industries and highlighting some of the typical challenges associated with each type of analysis. I'd like to start off with a few definitions. First, computational aeroacoustics is the art of predicting noise produced by turbulent flows. Covers all aerodynamic flows, including wind noise. It does require highly accurate spatial and time solutions. The small-scale turbulences must be resolved. Combining the required time and spatial requirements with reasonable simulation turnaround can be challenging, especially when you have design deadlines to meet. Fan noise is more specifically the prediction of flow-induced noise created by the presence of a rotating object and its interaction with the air and turbulent structures around it. This would be the focus of today's presentation. So why are we considering fan noise? In the industrial space that we'll be talking about mostly, the regulations dictate maximum sound levels these machines can generate. That's for the protection of the workers and for others in the vicinities of these machines while they're operating. The contribution of fan noise is generally the most dominant noise source of these machines. The application of this methodology can also be applied directly to automotive cooling fans. And with the increasing use of electrification, especially of the powertrain, fan noise is quickly becoming one of the largest customer complaints. Testing is very mature and a reasonably fast method to evaluate fan noise. So why should simulation be used? Well, for one, prototypes are not inexpensive, and there is growing pressure to reduce the number of physical learning loops in the development process. Production intent hardware is generally not available for prototypes, and some type of rapidly built parts must be substituted, which increases the uncertainty. Adequate chamber time is expensive and in high demand, limiting the number of interactions and iterations that can be evaluated. And as with all types of physical testing, gaining valuable insight into the mechanisms and the broad understanding of the acoustic and bulk flow results are not possible. Physical testing provides only a pass-fail result at various predetermined microphone locations set up to meet a specific test standard. In this next section, I'll provide a brief overview of the Lattice-Boltzmann method and ultraFluidX. ultraFluidX is a Lattice-Boltzmann-based computational fluid dynamics solver. So what makes that different from Navier-Stokes solvers? The Lattice-Boltzmann method discretizes the fluid volume into an orthogonal matrix of voxels and connects those voxels nodes and creates this lattice. During each time step, the movement or streaming function is solved with the collisions on each of the lattice links, with the behavior being controlled by the fluid viscosity. The Lattice-Boltzmann method is inherently trying to balance temporal momentum on the lattice, and because of this, the collisions and stream functions need to be explicitly handled. This also leads to the requirement that the lattice size must be octree-based, and each lattice size change must be a 2-to-1 ratio. The solver is only working towards a momentum balance on the lattice at each time step and is not solving for the traditional scalar properties such as pressure during the process. Because of this, the mathematics break down to a simple algebraic equation and do not require the use of partial differential equations. The macroscopic properties can be derived from momentum and particle distribution functions. With Lattice-Boltzmann being explicit in time, in space, and local in space on the lattice, it lends itself massively to parallel executions and why Altair has chosen to run on GPUs. This will be discussed further and later in the presentation. As mentioned in the previous slide, ultraFluidX is a lattice-based Boltzmann solver approach to solving isothermal, fully transient 3D flows. It uses a Smagorinsky LES turbulence model to model subscale turbulence away from the wall and a proprietary turbulence-based wall model to model the flow near the wall. The pre-processing requirements are highly simplified and will be discussed in the next slide. Volume discretization is handled automatically by the solver, and the case setup is handled with a simple, easy-to-use GUI we call virtual wind tunnel. World-class post-processing capabilities are also available, and our output formats are not proprietary. Automation of the post-processing can easily be achieved through the use of English-readable script files that are capable of generating hundreds of images in less than an hour. ultraFluidX is also executed on CUDA-supported GPUs for extremely fast turnaround and will be discussed in more detail shortly. ultraFluidX does not require a traditional volume mesh, and therefore the surface mesh preparations are very simple and straightforward. The surface mesh only needs to adequately define the geometry and should capture the appropriate features and radii without regard to traditional quality requirements. Since no volume mesh is grown from the surface mesh, strongly skewed elements and non-conformal meshes are acceptable. In fact, the advanced discretization techniques used in ultraFluidX prevent trapped fluid nodes, and gaps smaller than the local voxel size will not cause leakage of the fluid. This results in a very short model preparation time and simple part replacements. We have also worked extensively with other pre-processed simulation files from other solvers and generally have been able to directly simulate without modifications. Since ultraFluidX is solved explicitly in time and locally on the lattice, it lends itself well to massively parallel operations and is a perfect match for GPUs. While the processing power of a single GPU is less than that of a CPU, the sheer compute density advantages of the GPUs more than makes up for its lack of speed. To compete on CPUs, you would need a full rack of high-end CPUs with very high investment costs and energy consumptions to compete with a simple, low-power 4U server of 8 V100 GPUs. Altair's licensing model will also not limit your ability to run on as many GPU cores as you desire. Current GPU technology allows us to turn around fan noise simulations in approximately 15 hours. For quick design studies where absolute accuracy may not be as critical, such as for ranking design choices, the turnaround can be reduced in half. Setting up and simulating fan noise cases is very straightforward and quick. With the limited surface mesh requirements of only capturing the geometry appropriately, the geometry to mesh can be done in as little as an hour. Working with the surface mesh and virtual wind tunnel pre-processing tool is very intuitive, and the ribbon-style interface guides you through the process. In the image shown here, the process is literally from left to right. If you are working with the virtual wind tunnel on the GPU cluster, submission of the job is just a single click. If you are working remotely, then exporting the two required simulation files, one containing the surface mesh and another containing the simulation parameters, and uploading those files and executing the run scripts only takes a few minutes. As mentioned before, with the massively parallel GPUs, a typical fan noise simulation can be turned around in very short order, typically less than 1 day. In this section, we'll quickly go over ongoing aeroacoustic development at Altair. Since the post-processing tools being developed for greenhouse noise are also being used for fan noise analysis, we have not only been working with real fans in industrial and white goods, we have also been working with real vehicles in collaboration with various OEMs. However, due to confidentiality, we are not able to show any of the results. The starting point for acoustics at Altair has been greenhouse noise, and more specifically, a generic test buck used to evaluate the A-pillar effects and study mirrors. Here we see on the top the setup of a simplified A-pillar and side glass model in two configurations, mirrors off and mirrors on, as well as the microphones on the side glass. In the middle row, we see the transient flow structures from ultraFluidX on the side glass. The side glass was isolated in this case, since the final objective was to predict the sound transmission into the passenger compartment through the glass. For more general noise cases, we are interested in validating the wall model on the flow structures and the dB maps. In order to capture the flow properly, we also need to model the wind tunnel, including the boundary layer profile and the turbulence intensity. The dB maps can be seen on the bottom row, and the comparison of the sound pressure levels between the mirror on and mirror off cases from the experiment. The most basic signal processing for aeroacoustics and fan noise is the fast Fourier transform, or FFT, on probe or microphone locations where the time-dependent acoustic pressures are converted into frequency domain. A few things to consider when performing an FFT are the sampling frequency of the time data, the block size used during the FFT, and the number of averaging blocks. The sampling frequency and the block size will determine the narrowband frequencies of the FFT result, and the number of blocks will improve the accuracy of the results. The second type of analysis allows the display of the dB maps onto predetermined surfaces where high-frequency surface data has been generated. The same type of controls used in the probe FFTs can be applied here as well. The Altair acoustic post-processing tools provide adequate control over the parameters to generate sufficient data for acoustic analysis and can be used standalone or in additional tools as needed by the customer.
大家好，我们主要分这个演讲分成大概2个主要的部分。前半部分呢是关于奥泰尔就是风扇噪声的一些解决方案，以及相关的 UFX 就 ultraFluidX 的一些特点以及它的应用方法。那么后半部分呢是关于一些具体的风扇噪声的一些案例。那么前半部分如果大家有什么问题的话，我们现在稍微停顿一下，大家有问题可以提，然后 Kevin 呢会在线为大家解答。如果大家没有什么问题的话，我们就继续了。等所有的这些片子都讲完以后，我们后面可以集中进行回答。
At this point, I'd like to ask if there are any questions. Now in this final section, we will explore 4 customer cases where ultraFluidX was blindly correlated to customer data. 3 of the cases are axial fans, and 1 is a squirrel-type fan found in automotive heating and ventilating ducts. Before starting fan noise simulations, most inquire about the accuracy of predicting the fan performance. On this slide, you will see 2 different types of fans. One is a resin-filled fan with an aerodynamic blade shape. The other is a stamped sheet metal blade with a sharp leading and trailing edge. Both fans exhibit a distinct transition from axial to radial flow, and the fan performance is accurately captured to within a few percentage. The most basic post-processing for fan noise is performing an FFT on specific microphones or probe locations. In this case, we were asked to model an axial fan on a test stand that was measured by 4 microphones in an anechoic chamber. We placed the 4 microphones in the simulation at the same locations as the microphones, as provided by the customer, and performed a basic FFT post-processing script. Generally, a simulation of this magnitude can be completed in 6 to 8 hours using ultraFluidX to obtain around 3/4 of a second of usable acoustic sampling. The customer was interested in the absolute values of the overall sound pressure levels and in the blade pass frequency along with its harmonics. Unfortunately, for confidentiality reasons, I cannot show the sound pressure levels nor the correlation to the test data. However, I assure you, we have complete confidence in our results. Most fans don't operate in the open, and they're enclosed with some kind of a machine. In this case, we worked with a customer to model an industrial machine with a very complex underhood. The detailed geometry supplied not only contained all the machine components, but none of the details were sacrificed for the simulation. Detailed finger guards near the fan itself were resolved as they contribute to the broadband noise of the machine. Foam insulation, including acoustic material, is present and was modeled. The machine also has 2 heat exchangers, and they were treated as porous media in the simulation. You can see from the animation on the bottom right side that the acoustic waves propagate out from the machine, as well as the bulk flow you can see migrating along the floor. The machine details are not extremely important, but a few parameters may be of interest. The fan is approximately 0.6 meters across and similar in size to a highway fan truck. The tip speed is typical for a ground vehicle, and the microphones were, in this case, 7 meters away from the exterior surface of the machine, and 3/4 of a second of acoustic data was analyzed. The challenging aspects of the simulation were obviously the complexity of the machine, the acoustic insulation panels, the distance of the microphones from the machine. In this case, we did not use any transmission algorithm such as FWH or light hill and relied instead on the solver itself to carry the acoustic energy to the probes. The customer in this case supplied us 1/3 octave band data shown above in gray from their test after we supplied our analysis results shown in blue. The overall sound pressure of the machine in the simulation matched very well to the customer supplied data. Again, a different machine was blindly correlated. In this case, the machine is over twice as large as the machine in the first case, with significantly more underhood volume and complexity. The fan diameter is 1 meter, driving 3 heat exchangers directly. There were 2 additional heat exchangers placed over inlets of the machine as well. There were again 5 microphones, and they were placed 7 meters from the exterior surfaces of the machine, and 3/4 of a second of acoustic data was analyzed. Due to the size of the machine, the computational domain was nearly twice as large as in the first case. Very challenging aspects of this simulation were the complexity of the machine, the acoustic insulation panels, the distance of the microphones, and obviously the sheer magnitude of the machine itself. As with the previous case, we did not use any transmission algorithms such as FWH or light hill and relied instead on the solver itself to carry the acoustic energy to the probes. The customer in this case supplied us overall sound pressure level at each microphone, represented above in black, from their test after we supplied our analysis results, presented in gray. The overall sound pressure level of the machine in the simulation matched very well to the customer supplied data. In this third industrial equipment case, an indoor machine was modeled that has 2 rotating fans and 2 heat exchangers. The heat exchanger package is mounted on the top of this unit, which stands nearly 2 meters tall. The case presents challenges in that there are 2 large rotating zones that are required to have accurate acoustic properties, and 2 heat exchangers on top of the machine that have to have accurate propagation of acoustic energy as well. And there's inlet louver acoustic insulation panels. The acoustic test standard used for this machine is slightly different than the acoustic power, than the other machines, and it's acoustic power. And it's based on the calculation of 9 microphones. These microphones are then averaged over the 5 faces surrounding the machine, multiplied by the face areas. And this calculated power level for each face is an average to determine the overall sound power level. We were able to predict the sound power level quite accurately. In this fourth case, We modeled a squirrel cage blower typically used in automotive heating and ventilation systems. In this case, the fan blade assembly contained around 40 blades with a thickness of around 0.5 millimeter. Microphones were placed around the fan assembly as shown above, and the simulation was set up to replicate the test as near as possible. From the data analysis above, the 30 seconds of test data is represented in black, whereas the approximately only 1 second of simulation data is presented in red. Because of the discrepancy in the number of averaging blocks due to the significant difference in signal sampling length, we expect the simulation data to contain more noise than the test data. The simulation was set up to minimize runtime since the customer is only interested in frequencies below 2,500 hertz. In this case, the customer was pleased to see we captured the blade pass frequency around 750 hertz. And overall sound pressure levels matched very well. In summary, ultraFluidX, a lattice-Boltzmann method base solver, is perfectly suited to study fan noise. Its inherent time-accurate transient model is ideal for complex turbulent flows. It is uniquely able to quickly solve these transient flows in hours for industrial and automotive fan applications. Because of the lack of acoustical numerical dissipation, ultraFluidX is able to directly model the acoustic propagations, and no other acoustic transmission models are required for most applications. The rapid turnaround capability allows for an accelerated learning loop and can improve the design cycle. In many cases, a new design can be set up in a single day with results the following morning. However, the best news is that ultraFluidX has now been validated blindly across several types of fans, in several types of products, across several industries. We have also gained significant confidence over the past 6 months through many of the validation exercises we have done with several customers worldwide, some of them blind, and with impressive results. We also have learned through the process the approach to provide good insight to how to help customers improve their designs. The results of this work, along with our expertise, has led us to an important resource to our customers. We have senior experts with years of machine design focusing on reducing fan noise. We can collaborate on your projects to improve your designs, and Altair's licensing models, methodologies, and technology can help you succeed. Because of our unique licensing model, we can offer significant cost savings, and combined with our rapid turnaround, allow you to explore large design spaces to optimize your design. Recognizing the fact that GPU availability may be challenging for some customers, we offer access to GPU hardware, either through a secure cloud virtual appliance or on-site cloud solutions for maximum confidentiality. Again, I'd like to reiterate that we have validated our solution through several OEMs on several different types of fan noise applications. I want to thank you for your time and attention.
我们演讲的内容就到这里为止。然后呢，我会选一些大家提出来的问题，我先给 Kevin 解释一下，然后他会回答，到时候我再给大家做进一步的解释吧。首先是这位曲先生提出来的问题，是关于后处理方面的，我先给 Kevin 翻译一下。Hey Kevin, can you hear me? Hello Kevin, I cannot hear you.
Can you hear me?
Yes.
Okay.
So the first question is about the post-processing. The question is, he said, our post-processing can show the sound pressure level and also the position or the location. But it's difficult to know why the noise is created or the mechanism of the noise. So is it possible to use our post-processing to show the detailed mechanism and understand why the noise generates and locate the noise source?
It looks like he's asking two questions. One is vibroacoustics, mechanical vibration, which would be NVH or vibroacoustics, and that the transient loads would have to be put into an FEA or some other type of solver to figure out the vibroacoustics. But from the aeroacoustic side or the turbulent flow structures creating noise, right, currently at this point you'd have to use band pass filtering on sections or on the fan itself to try to look at where the noise might be generated. There are some additional post-processing tools that are still being developed to be able to locate the flow-induced noise sources, but they're not available at this time.
我大概回答一下，就是刚才这个问题呢，后半部分他也因为有人给翻译，他也看到了。那么主要分为2个部分，第一个就是结构振动的。那么对于我们的软件来说呢，我们的软件主要是一个流体的解决方案。如果需要考虑结构振动、结构强度的话，可能需要 FEA 的这种方法去辅助。那么另外呢，对于噪声的定位以及它的产生的机理如何去研究呢？大家可以看到我们刚才所有的这些片子展示的后处理呢，基本上都是像曲先生所说的，可以定位它的风噪的大小以及它的位置。但是呢，大家可能更关心的是它风扇噪声发出的原因。那么刚才 Kevin 也说了，我们现在有新的这种后处理的办法，比如说是 band passing 这种，就是相当于滤波的一个过程。我们可以把所关心的波段的噪声的能量呢过滤出来，然后把它返回到时间序列上。我们可以去通过动画或者一些其他，比如说 dB 啊等等，去看一下它的这个噪声到底是怎么发出来的，是从哪里产生的。那么另外呢，我们刚才在片子里头大家也可以看到，我们目前还在开发一些新的像信号处理啊、噪声的后处理的等等一些工具，目前还在开发当中。当然，根据这个工业应用的需求呢，我们也会给大家提供越来越多的工具。然后第2个问题，Kevin.
Yes.
So the second question is about what's the difference between ultraFluidX and PowerFlow?
Yes, I see. There's 4 parts to that question.
Yeah, let's do one by one.
Exactly. The biggest difference of ultraFluidX to PowerFlow is going to be the speed at which you can turn around simulations. I don't want to get into like all the geometry prep, but abutting surfaces and abutting faces and trapped fluid voxels are not present. So the pre-processing is very quick, and the turnaround time on the GPUs is going to be half to a third of the time that it would take with a CPU-based lattice Boltzmann code.
So Kevin 刚才回答呢，它的一个最主要的一个差别呢，因为 UFX 和 PowerFlow 呢，我们用的是非常相近的原理，是 LBM， 但是它的这个最大的区别是，UFX 呢是基于 GPU 开发的，所以他想说的是我们的这个计算效率呢是远远高于 PowerFlow 的。另外他也提到呢，前后处理呢，我们也进行了一些优化，在一定程度上效率也是高于 PowerFlow 的。
And then cis noise, the difference between Altair, ultraFluidX, and cis noise. Are you still talking, Long?
Yeah. So Kevin, you already understand the question, right? You translate.
Yes.
Google. Okay. So
yeah.
Let me just explain. The second question is about how to understand the difference between ultraFluidX and cis noise.
Yeah, I'm not familiar with cis noise, so I can't comment on that. So I couldn't tell you.
不好意思啊，就是 Kevin 对 sys noise 不太熟悉啊，没有办法去帮大家回答这个问题。Okay, let's go to the third question. Is there any limitation for the fan noise size?
We've tested fans down to about 28 to 30 millimeters. As you reduce the fan size, the voxel size becomes smaller because it's explicit. The time step also becomes smaller, so the amount of computation time goes up. For a 4 centimeter fan, for an industrial fan, we're looking at about a half a day of simulation time. For something around 4 centimeters, we might be looking at 4 days of simulation time. A 25 millimeter fan might take 5 to 7 days. So as the fan gets smaller, the computation time goes up very quickly.
OK，Kevin 的回答是这样的，就是对于风扇的尺寸来说，刚才我们的片子里头也可以看到，那么大的风扇肯定是没有问题。那么小的风扇呢，我们现在已经尝试过做过几款，比如说有28毫米的、30毫米的这种小风扇。那么它的最大区别是什么呢？当风扇特别小的时候，我们需要去划分更小的空间网格，我们这里叫 voxel， 所以它的尺寸呢，网格尺寸会更小。那么同样会带来时间步长也会减少，变得更小。所以呢，去模拟同样一个物理时间的话，你会发现你的计算代价会提高很多。比如说我们在片子当中看到的一些工业用的大型的风扇，比如说这种制冷风扇，那么它一般在半天左右，比如说5到10个小时就可以完成。但是如果40毫米的这种40毫米，就是问题当中提到的4厘米的这种风扇呢，它的预估大概可能需要4天左右的时间。如果到25毫米这种级别的话，可能要5到7天左右的时间。Okay, Kevin.
And for 20 to 20 frequency. Yeah. Google Translate does a pretty good job here. So from 20 to 20,000 hertz, there's no technical reason why that's an issue. We filter out everything below 10 hertz in the simulation. Generally, we're looking at 100 to around 5,000 hertz. The only thing with 20,000 hertz is the resolution required to get that. If you're talking about the 4 centimeter fan, you already have the resolution to get that level of frequency. If you're talking about an industrial size fan, then we wouldn't have that type of resolution to get that high of a frequency. So as the fan got smaller, then the frequencies that you're going to capture obviously are going to be increased, and 20,000 shouldn't be an issue. We've never gone that high, but the sampling frequency and the voxel size would definitely be there for a 4 millimeter fan or 4 centimeter fan to at least have the data up to 20,000 hertz.
那么 Kevin 的回答是，关于这个问题，就是风扇20赫兹到2万赫兹的频率是否能够捕捉的话，那么技术上来说是没有问题的。对于工业上用的大型风扇呢，我们一般关心的是比如说1000到5000赫兹的这个频率段。但是对于这种小风扇来说，当然我们要关心的是更高频率。那么对于低频来说，我们只要捕捉的时间足够长，就是计算时间足够长的话，我们可以捕捉到最低10赫兹左右都没有问题。那么对于高频来说，只需要加密它的这个空间的网格，并且呢，我们的这个采样频率要足够高。对于20千赫兹，也就2万赫兹的这个频率呢，理论上或者技术上来说是没有问题的，只是计算时间可能会稍微长一些。大家还有其他问题吗？ 如果没有问题的话，我们今天的研讨会就到这里结束。Thank you, Kevin. So,
Yeah, you're welcome. Thank you.
谢谢大家。